All right, we're back again. Lucky you listening to me. Second part of this talk, largely going to cover carbonatites, diamonds, and pegmatites. So quite a diverse range here. But first, the weird and wonderful carbonatites. These are some sort of magma that is predominantly carbonate material. They're very weird and poorly understood. And so they usually occur, well, the most common ones are in Africa. And they occur with alkaline complexes or as seals, dikes, or small plugs. But it's only the intrusive carbonatites that are associated with economic mineralization. And because they're predominantly carbonate makeup, they have very low temperatures of crystallization, around 500 degrees. And we can get deposits that form as either primary igneous minerals or as replacement within or exterior to the intrusives. And you can further subdivide carbonatites based on the dominant carbonate mineral, calcite, dolomites, magnesium, calcium carbonate, or anchorite, iron carbonate. So 50% of all known deposits occur in Africa, mostly associated with the East Africa Rift. And formation is controlled by fractional crystallization, unmixing, or immiscibility, like I covered in the last talk, carbonate, silicate-rich melts. And carbonatites are inferred to form by low-degree melting in the mantle at very high CO2 conditions, and possibly related to variability in fugacity, but they're very good at carrying elevated rare earth element concentrations, particularly the light rare earths, and also they host them in minerals that are a bit easy to extract rare earth elements. Remember that part of the problem with the not so rare earth elements is that they can be very difficult to extract. So we can get significant element concentrations in things like copper, rare earth elements, iron, titanium, vanadium, uranium, thorium, and zirconium. And we can also get industrial minerals like vermiculite, apatite, fluorite, barite, as well as limestone, which is commonly used for a variety of processes. I'm just going to show you how weird they are as carbonate lavas. We can look at the main active carbonatite volcano in East Africa. And they are very viscous lavas. And so they kind of just look like mud. So we have a look in this
type of rock
YouTube
called carbonatite. When it comes to contact,
just go back
the
a bit.
active volcano that belches out black lava rich with a type of rock called carbonatite.
So as you can see, they're very weird, very runny. We see all this black material here is what this carbonatite lava forms as. So quite unusual, very low temperatures, highly viscous, and yeah. So carbonatites, there is two main current hypotheses about how they originate and in association between alkaline rocks and carbonatites, or ARCS. So the first one is the plume model. So the alkaline and the carbonatites are derived from the mantle plumes, just as sort of simple, deep mantle sources. Alternatively, they could be in the deformed alkaline rocks and carbonatites model. They derive from melting that involves deformed alkaline rock, carbonate material that was carried into the lithospheric mantle during an ancient subduction episode. So it's hard to fully tell how they are forming. As we say, we know that they're mantle derived. We need high CO2 concentrations in the mantle to produce predominantly carbonate-rich content. And so this is something that a lot of people are still actively trying to understand. So in one case, we must have a deep mix source of this CO2, The alternative is we're actually essentially recycling material. So here's the two types. So here's a plume mantle. We have convecting or rising hot magma, and it interacts with a source in the mantle, which is rich in CO2 and other carbonate material, which can then drive our carbonatite magma. This is based on example in the East Africa rift, where we're rifting lithospheric mantle in cratonic crust, so it's very deep sources. Another alternative is that we've actually buried this material deep into the lithosphere, or it's actually actively formed, potentially through metasomatism or something like that, in the lithospheric mantle, and then the hot magma, when we actually stretch this lithosphere, actually melts and drives the carbonatite. So very weird, very cool rocks. Yeah, everyone's still scratching their head. This is what one might look like when it's an intrusive phase. So, you know, they're being quite heavily explored at the moment in association with the drive for critical metals, particularly rare earth elements, for mobile phones, electronic vehicles, touchscreens, etc. Very, very beneficial for that. There's some in Australia. I know one in Northern Territory, which is quite prevalent rare earth deposit, but again, the main stumbling block is extractions and China's geopolitical control. In this example, we have monticelite with apatite, pyrochlore and latropite, and latropite is a niobium titanium iron oxide. This one's from Oka in Canada. So weird associations. Apatite is a phosphate mineral, remember? But these are the sort of ore minerals that we can form, and it's okay that I don't expect you to fully remember these, but pyrochlore, sodium, calcium, niobium oxide, bastinacite, cerium lanthanum, latropite, calcium, sodium, niobium. This is orthorhombic. We've got it as carbonates or as oxides, so it's quite easy to get high concentrations of these particular rare earths. We also get apatite, so phosphate, anatase, titanium oxide, and then we can also get zircon, bdelliite, so zirconium-rich concentrations, as well as magnetite or monazite, where we can get other rare earth elements. So we can then also get replacement minerals, because remember when we talk about skarns, carbonate rocks are alkaline and they can be very highly reactive. So we can have the opposite process in a skarn. We might actually cause it as a reaction with host rocks or fluids. So we might get fluorite, vermiculite, bornite, chalcopyrite, and other sulfides. And then we get residual minerals, anastase, pyrochlore, and apatite. And we have a series of gangue minerals, which are mostly carbonate. So calcite, dolomite, siderite, anchorite. We also might get some common rock-forming minerals, biotite, titanite, olivine, and quartz. So very weird, but increasingly important style of ore deposit. Okay, the next one, and something that can be associated, at least in Africa, with these big cratons, what we call kimberlites and lamporites. So these are mantle-derived potassic igneous rocks. And the advantage is they're coming from great depths, greater than 150 kilometers, and they form in very narrow pipes that taper at the surface due to their high volatile content. So high water, high CO2. So kimberlites actually produce hugely explosive eruptions. It's not clear that we've ever really recorded one, so it's a bit of an unknown, but they are very interesting rocks. They're highly heterogeneous, they're full of xenoliths, and that's why they commonly carry diamonds, and they move very quickly. People think they move almost at the speed of sound from 150 kilometers to the surface, therefore the diamond can't back react. So the carbon source is debated. There's multiple origins. It comes either from the upper mantle. Sometimes we also see recycled carbon, and we can tell by different isotopic signatures if it's coming from organic material or it's just residual carbon within the earth. And most of the old ones have a distinct older carbon signature, but some diamonds have young organic material. So they are wrapped rapidly like a cell and force carbon to be reserved as diamond. So that's one of the important factors and why we're so sought after. Here's an example of one from Transvaal. So we have this pipe that's tapering as it gets higher. We have a crater lake, and then we have little tuff rings where we've had erupted material land. And essentially, people are looking for, the diamonds in the pipe, sometimes maybe in the tuff ring. And we get them as xenoliths, and they're usually incorporated with things like garnet leucolites, very deep sourced material that are coming from the base of cryptonic lithosphere, where we're actually maintaining diamond stability right at the bottom of the lithosphere. Here's an example of a lamproite tuff from the Argyle diamond mine, very famous diamond mine that's no longer active, the pink diamond, of course. We have fragmentary material throughout. So lamproite's slightly different. The Argyle diamond is a lamproite. It's an ultrapotassic mafic igneous rock. They're typically dikes of pyroclastic flows. People think that the potassium, we have these areas in the lithospheric mantle which are superhydrated with forming a mica, much like biotite, called phalogopite, and then that's remelted to produce these material. But they're ultrapotassic, but they're also predominantly ultramafic. So we have this metasomatized lithospheric mantle that's driving it, largely through phalogopite, so potassium, mica, like biotite, but rich in titanium as well. And so these form Mar-like craters, like I showed before, and we get xenocrystic diamonds because, again, they move very quickly. So here's a beautiful example of a kimberlite. Here's a big megacryst of garnet. So these are the sort of xenoliths you see, or xenocrysts in this case, or foreign crystal. We have fragmentary material of all sorts of things. Here's some other rocks. Could be country rocks, could be diamonds. I'm not sure if that's a diamond. So very heterogeneous, complicated, and the diamonds are derived from material largely peridotitic or eclogites, so mid-ocean ridge material or peridotites that are formed in the base of the lithosphere, where we have little bits of carbon that's been introduced, and we have the right pressure, temperature, and redox conditions to allow carbonate to form and be stable. And so as these kimberlites and lamprophytes move to the surface very quickly, they might intersect these horizons that have diamonds, include them as a xenocryst, and then train them to the surface, as well as these mantle xenoliths. This probably formed at potentially 200 kilometers. This large garnet gives us a window into what it's like in the mantle. So here's just showing where they are, predominantly cryptonic lithosphere, because that's where diamond stability is preserved, where the lithosphere actually gets to 150 kilometers and the diamonds can sit there stably before being entrained in this kimberlite. So these are the ones to look for, guys. They're highly valuable, especially if you can find a new pink one. There's Argyle there, no longer being mined, but the famous pink diamond, which is worth a lot of money. But most deposits controlled by De Beers and related to Southern Africa. Okay, sapphires and rubies, also very pretty, derived in a similar way, but their stability is more favourable than diamonds, so they can form more prevalently. We just need to get the gem quality. Luckily for us in New England, There's quite a lot of sapphires. Sapphires is the blue corundum, and very proper for gem fields. There was a few mines that were active, and so I'm sure a lot of you that are interested in that, you should either know about it or come and maybe have a look for them. They're mainly present in reworked alluvial material, where we can concentrate the sapphires into gem bands. They occur with large zircon. There's also diamonds in the New England, which are slightly enigmatic, but unrelated to these sapphires. So they've traditionally been interpreted as xenocrystics, a similar way to the diamonds, but people have thought that they actually might be magmatic. Their high temperature of formation is consistent with an alkali host, and they crystallize at these 685 to 900 degrees. So ones up here are related to these plumes that are bringing material up and then eroding away. So here's a schematic diagram showing some of the common New England ones. Here might be a pipe of a alkali eruption, and Braemar is quite a prominent one, but we have these volcanic horizons, and we have sapphires being reworked into the alluvial material at the base through paleo river channels, and we can go and pan and find them. So they've come out of this specific mafic rock. Okay, finally, pegmatites, another increasingly important deposit type. A pegmatite, by definition, is just a coarse-grained igneous rock. Here we have a granite of sort of typical grain size. We have extremely coarse-grained crystals defining the pegmatite. So, by definition, it can be a variety of compositions, typically in granites, and they form these sort of dikes or veins. It's quite common. And how they form is that they're the last little bit of liquid. They're very water rich, and therefore they can form crystals bigger than the host granite. So there's a difference in water content between here and this one. Because they're that last bit of liquid, they concentrate metals that are incompatible, do not want to be going into the typical minerals of a granite, and they concentrate into the pegmatite or into the fluids of the pegmatite, and we can form things like beryl, topaz, tourmaline, spodumene, or other lithium minerals, as well as our standard quartz feldspars. So they're defined by their coarse grain size. They can commonly show these really cool textures called graphic intergrowths. Here's an example. Here, so it's so described because it kind of looks like petroglyphic or ancient Egyptian writing. You can always get a presence, and this is related to the actual cotectic, or the simultaneous crystallization of quartz and cave feldspar together, and they form these complicated intergrowths called graphic intergrowths. Very, very stunning, impressive textures to see. We have the quartz here, and then we have the milkier cave feldspar. 99% of pegmatites are minimum granitic liquids, and what we mean by that is just that they have equal amounts of quartz, cave feldspar, and plagioclase. But rarely pegmatites can contain minerals like beryllium, can contain elements like beryllium, boron, tantalum, lithium, and cesium, as well as nice myrolithic cavities, so gaps or gas areas of the pegmatite that can contain gem quality minerals like beryl, aquamarine. So, like I say, the standard interpretation is these final bits of the liquid, but there is controversy surrounding how exactly they form. They have to involve some degree of fractional crystallization to preserve that limited, the final components of the magma. But people suggest that they might crystallize down to 450 degrees. So 200 feet below the solidus of most magmas, which is around 650. So people think that these compositions are actually highly fluid rich and actually start to behave as a fluid after we've had this concentration from fractional crystallization. And we have this low temperature crystallization in fluid rich environment. We might also have things like boron, fluorine, water, and it enables the growth of large crystals, sometimes in graphic textures, and the concentration of incompatible metals in minerals. So like I say, there are important bodies for lithium, where we can form spodumene, boron, tantalum, bismuth, and tin, also potentially rare earth elements. We're also important for industrial minerals, potentially topaz. Sorry, that keeps happening. It's very frustrating. Beryl. So here's some of these beautiful mineral specimens that you can find in them. Very spectacular rocks when you find a nice mineralized one. There's prominent ones in Western Australia. I know some of the students are actually going to go and work in some of these mines. So here's just a rundown of sort of minerals you can get, and they have a diverse application that is good from pegmatites. So some of the historic important ones, Brazil, Madagascar, but there's a lot going on in Africa and as well as in Australia. So watch this space, or for the people that are going into it, you'll learn lots about pegmatites. I know there's people looking all over to see if they have high concentrations of particular critical metals. So, excellent. Thank you all, and I will upload some more lectures tomorrow on superficial deposits, but these lectures should give you a good chance to work through some of the deposits like Mount Magnet, and as well as thinking about other components of the assessment.